Hello, hi, good people. We're starting chapter 6, linear transformations, and this is really I would have to say this is probably my favorite chapter of the whole topic. Anyway, linear transformations. So let's just start with what a transformation is altogether. Um, well, we're going to learn a transformation is basically just a fancy word for a function, but we'll explain. Anyway, uh, a functions that map a vector space V into a vector space W, which basically means um, a map is just sort of a fancy word for a function, um, and it maps something. So here's my domain V. The vector space V is my domain. The vector space W, that's the larger oval here, is my codomain, and the smaller oval is the actual range. So when the function takes vectors in V and sticks them into W, it happens to be that it only hits these guys right. It only hits these guys right there. Doesn't hit the entire W. That's what you're used to seeing, in algebra. We talk about a function and the range and so forth. Now, a linear transformation basically is just a function. What's um, what's special about it, or a little different than what we're used to, usually we have a function, we stick in a number and it spits out another number. That's typically we have for a function. We stick in a real number, it spits out another real number. Or now, what's different a little bit about a transformation is that the domain, first of all, it's not we're not putting numbers in. We're sticking a vector. My input is a vector. My output is another vector. So instead of my input being a number, my output being a number, my input and my output are vectors. That's one thing that makes it a little bit different than a typical function. Another thing is that usually the functions that we've always dealt with, uh, in a regular typical algebra class, is the domain and the codomain are kind of in the same world. Usually, it's the domain is real numbers and the codomain is real numbers, and the range is some subset of those real numbers. Well, here, the domain is vectors from a vector space V. The codomain is vectors from a vector space W, and these might be two totally different vector spaces, meaning to say the domain might be R3 and the range might be M22, or the domain might be P7 polynomials, less than 0, and the range could be whatever, it could be any kind. It could be a set of continuous functions, or who knows what. So the domain and the range may have, in a way, have like nothing to do with each other in a sense. It'll be totally different worlds. So when you take something from one world and send it to something from another world, that type of function is called a transformation. An example of a transformation, if those of you who've taken differential equations studied the Laplace transform, well, Laplace transform is really an example of this because it takes functions of t and it turns them into functions of s. And if you studied Laplace transforms, you know what I'm talking about. But that's why they call it a transform as opposed to just a function. But a transform is a type of function. Yeah, so it's an elite. It is a function. Now, what we start with a vector v, and we send it to a vector w. So we call vector w the image of vector v, or we could say that vector v is the pre-image of w. It's kind of two ways of saying the same thing. And let's look at an example of a function that goes. By the way, this is a transformation. Now, as far as linear transformation, we're gonna define that. But right now, we're just looking at transformations here, and we don't know yet or care yet about linear. So here we have example one. We have we have a vector v, which is v1 comma v2. So here, by the way, this example here is that the domain and the codomain happen to be the same vector space. And like I said, it doesn't have to be that way, but in this case, this example happens to be that it is. So so the first vector is, you know, the components of v1 comma v2, and we're taking a transform which sends vectors in R2 to other vectors in R2, and we're defining this transform that if we have a vector v1 comma v2, remember v1 and v2 are just scalars, are just real numbers. So t of v1 comma v2 is v1 minus v2 comma v1 plus 2v2, and that's just the way we define this transformation. So what I'd like you to do right now is find the image of the vector -1 comma 2, and then I want you to find the image of the vector 0 comma 0. Then I want you to find the pre-image of the vector -1 comma 11. So pause the video and work it out, and then we'll go over the answer. Okay, that's the end of the pause. I hope you enjoyed pausing. And here we go. So for the vector -1 comma 2, we have, so we say t of the transform of -1 comma 2 is -1 minus 2, because it's v1 minus v2, comma -1 plus 2 times 2, because you see up here we have v1 plus 2 v2. And if you put this all together, that becomes -3, and this here also this becomes +3, because it's -1 minus 2, and that's -1 plus 4, and there you go. Now the vector 0 comma 0, well, that's just going to be 0 minus 0, and then 0 plus 2 times 0, just a lot of nothing, and that winds up being 0 comma 0. And the vector the vector now we want the pre-image of -1 comma 11. So we want to find v1 and v2. So we're saying that t of the vector v, well, by the definition here is, and let me just highlight this right here, so we have it. The definition of this is v1 minus v2, v1 plus 2v2. So we're saying v1 minus v2 is my first component, -1, and v1 plus 2v2 is my second component, 11. Well, now we just do a regular good old-fashioned, you know, two equations, two variables, system of equations, you know, and we get v1 is equal to 3, and v2 is going to be equal to 4. 3 minus 4 is -1. 3 plus 2 times 4 is +11. So the pre-image of -1 comma 11 in is the vector 3 comma 4. Notice it says here single vector, because the pre-image, you know, function, to be a function, something has to have only it can only have one image, but you could have more than one pre-images. You know, just like the meaning to say, like we know with functions, the one input has to only have one output, but one output, a particular output could have several inputs. Anyways, that's a function. Now we're going to get to the headline topic, which is linear transformations. And a linear transformation, we're going to see, preserves linearity. Well, what does that mean? Here we go right here. This is what it means. So we're gonna talk about functions. Basically, when you have a vector space, we know that I could add two vectors. Well, if I add vector A plus vector B and I get vector C, it would be pretty awesome if when the image of A plus the image of B winds up equaling the image of C. That would be pretty awesome if that happened. When that happens, that's what makes it what. Or for example, if we know that in a vector space, I can double a vector. I can multiply a vector times 2. Well, it would be kind of awesome if I had a transformation where when I multiply the original vector by 2, So I get 2v. Well, if the image was also multiplied by 2, meaning the image of 2v was 2 times the image of regular v, then that would be kind of cool and awesome. And that is precisely what a linear transformation is. That's what I mean when I say it preserves linearity. So if I have t of u plus v is equal to t of u plus t of v, and t of cu is equal to c times t of u. And that is a linear transformation, preserves linearity. And like I said, these two vector spaces don't have to be the same. Don't have to be. Oh, this is, I like the way he puts it here. Operation preserving. That's kind of interesting. But that's really what I was just explaining. Now, notice that u plus v, those are two vectors. U plus v is a vector in vector space v. T of u plus t of v is a vector. This is a vector in w in the vector space w, and that's a vector in vector space w. So this here, even though I see a plus sign here and I have a plus sign over there, these two plus signs may not be exactly the same thing, because this is addition in my vector space v, and this plus sign here represents whatever addition means in my vector space w. And it's possible that in the two different vector spaces, addition is a whole defined differently, everything is different, but it doesn't matter. In addition, when I add two vectors in this world, it'll be the same as adding the two images of those vectors in the other world, whatever the codomain happens to be. And similarly, cu is a vector in v, because u is a vector in v, in vector space v, and cu is another vector in vector space v. But t of u is this whole t of u is a vector in w, and I'm multiplying that vector in w times the scalar c. So just be aware that when we do linear transformations, even though we're writing scalar multiplication, we're writing the same plus signs, really it's really analogous. It's the whatever addition means in that new world, or whatever scalar multiplication is in that new world. Okay, let's do another example. Let's look at the example we just had. When we did example 1, we had a regular transformation. We didn't discuss whether it was linear or not linear. But now we want to show that this transformation that we talked about in example 1 is indeed a linear transformation. I'm going to highlight it again because it's so much fun highlighting it. And there you go. And let's show that this quote preserves linearity. So the first thing I want to do is look at t of u plus v. Well, t of u plus v, that's t of u1 plus v1. Well, what is u plus v? U plus v, the first component is going to be u1 plus v1. The second component is going to be u2 plus v2. Well, t of that is going to be u1 plus v1 minus u2 plus v2, because I'm taking the first component minus the second component. And then it's going to be the first component, u1 plus v1, plus twice as much as the second component. And that second component is u2 plus v2. Well, once I crunch all this out, I wind up getting u1 minus u2, comma, u1 plus 2u2. And here I have v1 minus v2, comma, v1 plus 2v2. That precisely is t of u plus t of v. So I have it all separated out. It all works out cool and awesome. Now let's look at so that's the first criterion to be a linear transformation. The second criterion is scalar multiplication. And well, let's look at it. So cu is c times u1 comma u2, which is cu1 comma cu2. I just distributed it. So t of cu is t of cu1 comma cu2. And the definition of our function is that my first component subtracts the two components of from the original vector space, and my second one adds the first component plus double the second component. Anyway, when I do this whole thing, I can now pull the c. Everything here has a c in it, So I could pull out a C, but notice that U1 minus U2, that is, and U1 plus 2U2, that is T of U. So it all worked out. So we see that this is a linear transformation because it preserved that linearity, and it is awesome. Now, let's look at the next thing. Let's look at some functions which are not linear transformations. And this is going to be kind of cool and interesting. We'll see why. So f of x equals sine. So f of x equals sine x. This will be a function from R to R. And this is not a linear transformation because sine of a plus b does not equal sine a plus sine b. So booyah. Let's look at the next example. F of x equals x squared. It's also not linear because a plus b squared is not a squared plus b squared. In fact, you can even see with plain numbers. 1 plus 2 squared is 9. This is 3 squared, which is 9. And this is 1 plus 4, which is 5. So 9 and 5 are not the same thing. If 9 and 5 are the same thing, then your workday will be very short. Now let's go to example C. Example C is really interesting because f of x equals x plus 1. Well, believe it or not, this is not a linear transformation. Why? Because if I have f of a plus b, that's going to be a plus b plus 1. But f of a plus f of b is going to be a plus 1, b plus 1, a plus b plus 2. So you see, this is not the same thing. And that's kind of interesting because x plus 1 is a linear function, yet it's not a linear transformation. So a linear function, linear transformation does not necessarily make. So just because I have, see, sine x and x squared, of course they're not going to be linear. But x plus 1, that's now what if I had f of x equals 3x? Well, if I have f of x equals 3x, that's going to actually, if you work that out, that will be a linear transformation. So sometimes a linear function will be a linear transformation, sometimes it won't be. Now, I'll give you, I don't know, what I consider a hint, I guess. If you graph this function, f of x equals x plus 1, you get a line that does not go through the origin. Whereas if you graph f of x equals 3x, you get a line that does go through the origin. I wonder if that's important. Oh yeah. And what does that remind you of? It reminds me a little bit of vector spaces. Remember we said a line through the origin is a vector space, and a line that misses the origin is not a vector space? I'm starting to notice things going on here. Let's move on. Here we have some simple linear transformations. If suppose t of v is equal to the 0 vector, so all vectors in v just map into the 0 vector. Well, that will be a linear transformation. And suppose I just have the identity vector. So this obviously this only works for functions with a domain and the codomain are the same. But the identity function, the identity transformation, if you will, that is a linear transformation. And you can work out why that is. Pretty not hard to do. Okay. By the way, let's say I have t of 0 equals 0. Because all the vectors in vector space V just go to the 0 vector. But if I say t of 0 equals 0, they're not the same zeros because I'm taking the 0 vector in vector space V and mapping that to the 0 vector in vector space W. So they're both zeros, but they're not the same. The zero, each one is a 0 vector in its respective vector space, but it's not the exact same thing. Okay, let's look at some properties now. So here are some properties of linear transformations. As I said, t of 0 equals 0. But just remember, the 0 input and the 0 output are not necessarily the same 0. And t of negative v equals negative t of v, t of u minus v equals t of u minus t of v, and if v is equal to c1 v1 plus c2 v2 then t of v is going to be c1 t v1 c2 t of v2 ... Okay, let's prove some of these. So number 1, t of the 0 vector Well, the zero vector is the scalar zero times any vector v. But by definition of linear transformation, this is going to be 0 times t of v. Now remember, 0v is in the vector space v. T of v is vector space w. But either matter what, when I multiply a vector times 0, I get the 0 vector. But the point is that the 0 over here and the 0 over there are not necessarily the same 0, or not necessarily the same vector. Each one is a 0 vector in its respective vector space, but the two vector spaces could be totally different. So like I say, this could be the 0, this could be a 0 5 by 7 matrix, and this could be a 0, polynomial or whatever it is, or 0, vector coordinate where all the coordinates are 0. Anyway, t of negative v, well, that's negative v is the same thing as negative 1 times v. I could pull out the constant, that's my linear transformation criterion, and I get negative t of v. So that's kind of cool. So if I have the negative of a vector in v, that it gets mapped to the negative of the vector of the respective vector in w. And the third one, well, that's basically, again, we're taking the properties of vector spaces. T of u minus v, well, u minus v is the same thing as t of u, u plus negative 1 times v, which is t of u plus t of negative 1v, which is negative 1 t of v, which is t of u minus t of v. So it all works out. And the last one kind of also follows from just taking the two definitions and combining them. Anyway, let's move on. So however, there is tells you that a linear is determined completely by its action on a basis of it. Interesting. If you look at what it does to a basis, if v1, v2, vn is a basis for a vector space, then tv1, tv2, dot 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 is going to be tv is then that's going to be completely defined, because since v is a linear combination of v1, v2 through vn, so t of v is going to be a linear combination of tv1, tv2, and so forth. So that's kind of cool. But that's theory. Let me show you an example. So let's look at example 4. So t is a vector space. It goes from R3 to R3. Like I said, we're looking at a lot of examples where I'm going from the domain and the codomain are the same vector space. But like I said, it doesn't always have to be that way. Well, t of 1, 0, 0 is 2, negative 1, 4. T of 0, 1, 0 is 1, 5, negative 2. And t of 0, 0, 1 is 0, 3, 1. So that's what this is. And we want to find t of 2, 3, negative 2. Well, first of all, if you notice, 1, 0, 0, 0, 1, 0, 0, 0, 1, that's a basis for R3. So that's kind of cool. Now, negative 2, 3, negative 2, that's 2 times the first basis vector, 3 times the second basis vector, and negative 2 times the third basis vector. And we know from property 4, that's that famous property 4, it's just going to be 2 times the image plus 3 times the image minus 2 times that image, which just winds up being 2 times this guy and 3 times that guy and minus 2 times that guy. And then I wind up getting 7, 7, naught. Oops, I think I went to, okay, what did I do? So here, we're going to look at, this is kind of interesting here. We're going to look at a linear transformation, and you really, I guess I'm going to leave it to you to decide that this truly is a linear transformation. So t of v is a vector. Now v is a vector in R2, and t of v is a vector in R3. So here we have a linear transformation where the domain is R2 and the codomain is R3. And now what is the particular function? So the particular function is the matrix A times a vector V. So I have my vector V1, V2 in R2. This guy here is my matrix. And when I multiply this vector times this matrix, I'm going to get, since I have a 3 by 2 and I'm multiplying that times a 2 by 1, my result is going to be a 3 by 1. In other words, a vector in R3. So now what we want to do with this is we want to find T of V, where V is equal to 2 comma negative 1, and we want to show that T is indeed a linear transformation. And it's actually a rather important type of linear transformation, the idea of multiplying a vector times a matrix. So if V is equal to 2 comma negative 1, so T of V is the matrix A times the vector V, which is this matrix A right here, times the vector V, which is 2 comma negative 1. And when I crunch that all out, you wind up getting 630. And that's simple, straightforward matrix multiplication, which we've done a whole bunch of examples of that back when we were matrices. But notice that I took a vector in R2, and that was my input, and my output was a vector in R3. So there you go. Now let's just show that this is a linear transformation. Now the truth is, this is going to be true. Well, what's interesting here is that T of U plus V, well, that's just A times U plus V, because that's what this function is, which is AU plus AV, because we know that we can distribute. We learned that already back in theorem 2.3. And now I just redefine everything. AU is T of U and AV is T of V. Now T of CU, that's going to be the matrix A times the vector CU. But we learned you could pull a scalar out of a matrix multiplication, and we have C times T of U. Now notice here in part B, when we prove part B that this is a linear transformation, notice that there's nothing here which spoke about about the particular matrix A. There's nothing in this little proof here that spoke what. Notice we never really said what the proof doesn't really. What I'm trying to say is that this proof does not depend on what the particular matrix is. Meaning that if I have a function which takes a vector and multiplies it by a matrix, that will always be a linear transformation. It wasn't dependent on this particular matrix, but any matrix. And that's going to be a linear transformation. So if I have it, so if A is a 3 by 2 matrix, then AV is going to be a linear transformation from Rn to Rm. And there we go. So in fact, this is what we're saying right here. If A is an M by N matrix, then if I look at the function T of V equals AV, that will be a linear transformation from Rn to Rm. And in order to conform to matrix multiplication with an n by n matrix, so an n by 1 matrices represent the vectors in Rn, and m by 1 matrices represent the vectors in Rm. And this is an interesting remark here. The n by n zero matrix corresponds to the zero transformation from Rn to Rm. And the n by n identity matrix, In, corresponds to the identity transformation from Rn to Rn. It's good to know. Anyway, and here we go. So here's my vector V, which is V1 down to Vn. I'm multiplying it by vector space, by matrix A, and A is an m by n matrix. So there are m rows and columns, and I get this guy here. Now this here is a single vector. You see, this looks like it looks like a whole big giant matrix, but it's actually, this is just a one column matrix. Because when I add these guys up, A11 V1 plus A12 V2, dot, 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 I'm going to add this all up and get one number. So this actually is a single column matrix. Anyway, let's just do example 6. So we want to look at a transformation T of V equals AV, and A is, so we're looking at a few examples. Here A is a 3x3 matrix, here A is a 3x2 matrix, and here A is a 2x4 matrix. So we want to look at these linear transformations. So for A, because it's a 3x3 matrix, that means that the transformation is going to go from R3 to R3, and that's what it's going to look like. Now here, because it's a 3x2 matrix, that means we're going to go from R2 to R3. And here it's a 2x4 matrix, so it's going to go from R4 to R2. And that's what I was trying to say here. We're gonna stop here, and we'll continue in part 2. So let me stop the recording, and I'll see you guys real soon.